Hello, everybody, and thank you for coming to the Undergraduate Research Symposium. I'm Max Pezzelle, and today I will be talking about the classical double copy, which is the subject of my current research activities and of my Barrett Honors Thesis. I'm doing this research under the advisement of Dr. Joseph Foy at Barrett the Honors College and Tucker Manton from the Department of Physics. I'll begin by discussing what the classical double copy is. It is a relation between gravitational fields, solutions to the Einstein field equations, which are metrics of spacetime, and gauge fields, the solutions of the Yang-Mills equations. It was first formulated in 2014 as a classical analogy of a phenomenon observed in quantum field theory. Namely, what some workers discovered was that pure graviton scattering amplitudes can be rewritten as the product of two pure gluon amplitudes. The classical double copy described here was formulated as a possible way of understanding that original double copy relation. It can be written schematically as gravity equals gauge theory squared, and it offers a new way to do calculations in general relativity faster, as well as offering a new view of gravity. I'll speak more about its importance to physicists overall at the end of the talk. Here I give an outline of the formulation found in 2014. Suppose that you can write the metric of the spacetime you're analyzing in the following way, where eta is the Minkowski metric, phi is a scalar function, and k is a null vector, which means that the inner product of it with itself is zero. K here also has the special property that it is null with respect to both the full metric and the Minkowski metric. This is the consequence that the inverse metric is given by the form on screen. Notice that this is a non-perturbative metric. It may look perturbative since it is written as the Minkowski metric plus another field, but this is an exact solution. Metrics written in this form are said to be in Kerr-Schild form. Given this metric, one can write the Ricci tensor as the form on screen. An interesting note is that it's linear in the graviton field. Without loss of generality, we can suppose that k0 equals 1. And furthermore, suppose we're analyzing a vacuum spacetime whose metric does not depend on time. The vacuum field equations then state that the Ricci tensor is 0. Then the field equations imply that the field phi k mu solves the vacuum Maxwell equations, which is really remarkable. And it's this fact which is known as the classical double copy. Now that I've shown that demonstration, I can give a step-by-step guide on how to use the double copy to obtain the corresponding gauge field solution. Step 1 is to find a metric in Kerr-Schild form. Step 2 is to take off a factor of k mu from the graviton field. Step 3 is to exchange charges between the two theories, which for example means exchanging mass for color charge. And step 4 is to apply a gauge transformation to the gauge field if it helps with its physical interpretation. Importantly, one can follow this process in reverse to go from a gauge field to a gravitational field. This offers a new way to find solutions to general relativity from simpler theories. On this slide, I give a diagram that displays the terminology used to refer to the different fields at play here. Double copy refers to the graviton field, single copy the gauge field, and zeroth copy the scalar field. Many examples of the classical double copy have been found so far, and displayed here are several of them. A Coulomb point charge double copies to a Schwarzschild black hole, which makes sense given that Schwarzschild is the unique, spherically symmetric static solution to general relativity, while the Coulomb solution is the same thing, but for electromagnetism. The Kerr metric is the metric for a black hole rotating uniformly about some axis, and its single copy is an electric field plus a certain magnetic field. Interestingly, one can investigate a special solution in gravity called the Taub-Nut metric, and its single copy is actually a magnetic monopole, although there is a subtlety that I will get to on the next slide. I also add here that plane waves in electromagnetism double copy to PP waves, which are exact gravitational wave solutions. These are time-dependent solutions, and it's interesting that the double copy also works in that case. I mentioned that there's a subtlety with the Taub-Nut solution. It actually has a double Kerr-Schild structure. One can still follow a double copy procedure similar to the one described before, however, and find a gauge field solution given by A mu, and it's this field that displays characteristics of both an electric charge and a magnetic charge. It's also interesting to note that this whole analysis for Taub-Nut can be done in de Sitter spacetime, and this double copy interpretation can still be made. In addition to understanding the Taub-Nut solution over the past few weeks, I've also been studying some other things, which are listed here. I began my work by analyzing the metric given by that first line on screen, where A is a function that assumes various forms for different solutions. This metric is important in studies of black hole solutions and their single copy fields. I've also studied double copy relations between sources for black holes and their electromagnetic counterparts. For example, the source for a Schwarzschild black hole is a point mass whose stress energy tensor is given by that one on screen, while the source for a Coulomb field is a point charge given by that current 4 vector. And U is a 4 velocity in the rest frame of the mass on the one hand and the charge on the other. Notice that J becomes T upon switching Q for M and multiplying by an extra 4 velocity. This is a simple relationship, kind of like the double copy, but between the sources of the fields rather than between the fields themselves. My current research directions are listed here. In certain cases, the double copy can still be found even when the background spacetime is not flat, as I mentioned earlier. I'm currently investigating how this plays out more generally for metrics written in the form on screen, where g mu 0 is a metric for some general curved spacetime. I'm also beginning to study the wild double copy, which is a different double copy relation and written in the language of the spinor formulation of general relativity. Additionally, I'm working on extending the work done by several physicists here at ASU about the double copy for a non-singular black hole solution. I'll be analyzing a rotating black hole solution through the use of the fascinating Newman-Janis transform, and then looking at the horizon structure that results. I'd like to conclude by answering why other physicists should care about the results coming from studies of the classical double copy. First, general relativity is a beautiful and complicated subject, with some calculations taking very long times to complete by hand. Finding new ways to speed up computation time is always good. Secondly, studying and extending the range of the classical double copy may bring about the insight needed to understand the original relationship first seen between graviton and gluon scattering amplitudes in quantum field theory. Finally, the classical double copy may shed light on the nature of gravity and its relationship to gauge theories, which govern the other fields in nature. It is for these reasons that research in the classical double copy is interesting and why it will be exciting to see the results that come from studying it in more depth. Thank you for listening to my presentation, and I hope everyone has a good time listening to the others in this symposium.